Welcome to the presentation Programming Firmware for using the Small Device C Compiler, SDCC. I am Altbeer and I'm going to walk you through this presentation. The slide deck is available under altbeer.us/SDCC. So what is SDCC? Well, it is a C compiler. It's one that's specifically designed to work with certain microcontrollers. The MCS51 based microcontrollers, as well as a host of others that are listed here. You can download it and get information about it at the SourceForge page, sdcc.sourceforge.net. So to download and install it, SDCC is available for several different platforms, including Windows, Mac, and Linux. To download the version for your platform, you're going to go to SourceForge. The link is provided there. And in the case of Windows, what you're going to be downloading is a .exe, an executable file that will install a package of software on your machine, which is all the pieces of SDCC. In the case of Linux, the download is going to be a tarball. That's a compressed tar file containing the binaries and an installation script. So this is not a source thing that you have to compile. It is binaries and it has an installation script. And for many Linux distributions, binaries may already be available through your platform's normal application repository. An example I give there is for Debian-based systems or Ubuntu. You would just do apt install SDCC, and it should install it that way without having to download any extra files. Downloading the support packages. So when you're programming, you're going to need different packages on your system, regardless which compiler you're using. And for SDCC, what you need really depends on what your system is. For Linux, you're definitely going to want to get the Build Essential package, which has a bunch of build tools and C header files and whatnot for your system. This Build Essential is an Ubuntu or a Debian term, but all Linux operating systems, all distributions have a similar package that you can install to get your system ready for compiling. On the Windows system, the tools that you use are going to depend upon how you work with the code on your system. Me personally, I tend to work in a Linux-like environment when I'm on my system. And since I've done this since before there was a Windows Linux subsystem for Windows, I still use the packages I've always used, which is Git for Windows, installs a bash shell that you can use on Windows. The main.gw package gives you some compiler tools for working with makefiles and things that SDCC is not natively giving us or don't work as well as the SDCC tools. So I always install main.gw as well. And then in whatever environment you're working in, you're going to want to make sure you check your path in Windows. Windows paths are very particular. That way we tell it where our SDCC binary files are, where main.gw is, and where our makefile is that we're going to use. So depending upon your Windows system, you're probably going to have a different setup than this. And I'm assuming that anyone watching this video is not new to compiling or programming altogether. You're just wanting to learn about the SDCC specifics, and that's what this presentation is pointing towards. So I'm not going to go into any more detail there. So now we're going to talk about the chip software development kit at Toolchain. So depending upon which chip you're working with, you're going to need to download its SDK and its toolchain for firmware deployment. The different chips have different ways of handling this. In our case, for our examples, we're going to be using the CH552G chip And that particular chip has an SDK that's available through Blinken Labs, this GitHub page that's listed here. This SDK was originally written for Keel, and it was ported to SDCC by Blinken Labs. And it's going to contain all of our header files and different files that we need to include in our code to work with the specific chip hardware and layout. So based on the chip you're working with, you may have a different SDK that you have to download. SDCC does support a whole number of different chip types, as the previous slide showed. So just make sure you research your chip and download the correct SDK and the correct toolchain. As far as the toolchain goes for the CH552G chips, the manufacturer WCH makes a firmware upload program called WCH tool. It's only available for Windows, but it does work quite well under Windows. Or you can use a multitude of open source tools. There's Libra CH551, which works with these chips. There's the CH552 tool, which also works. And if you're working under Linux or some operating system other than Windows, you'll probably want to play with different tools to see which one is going to work best with your operating system and the chip that you're working with. Code file organization. So while code file organization is really a matter of the programmer's taste, I tend to keep the IC specific SDK libraries in their own directory, and then I'll include them from different make files as needed. And you can see from the file list on the right here that the include directory has a number of different files in it. This is all of these files are from the Blinken Labs SDK, and so this is the different header files and C files that I'll reference from my code. There's also a make file that I usually create when setting up a directory structure. I'll set it up to where the individual pieces of code have their own subdirectories with their own main.c and make file, so I can make just this piece of code, but then I'll make an overall make file that can do a make all, and we'll go into each one of these subdirectories and make the code. So that is the make file to compile everything. And then there's a common Makefile.include file. This came with the SDK, and it includes the different toolchain parameters. So that will be included in our code as we program. So let's take a look at the make files. So the make file for my firmware programs are pretty simple. So this is the make file that's in the directory with the main.c file. And it's going to give it a target name. So this is what the program name is that I'm going to be using. And it's going to call the main.c file. And I also call the debug file debug.c from the SDK that helps me debug code if there's problems when I'm programming it. And then I include the Makefile.include to get my toolchain set up. Now the make file that's in the main project directory, all it's really doing is going into each subdirectory from its current position, and it's looking for other make files, and it's going to execute them if they're there when we do a make all. And that's all it really does. So it doesn't have any specific parameters. It's just calling these make files. So the Makefile.include, that's for the toolchain, as I said earlier, this comes with the SDK, and we really don't need to change much about it. We just need to review it to make sure that we don't need to tweak any parameters based on our system. It's going to call out the compiler as SDCC and my WCHISP tool. Because I'm on Windows, that's the one I'm using. So you might have to change that if you're working on a Linux system with a different tool. And there's different parameters all throughout this file that you might just want to review and make sure that they're appropriate for the system that you're working on. So the main.c file, this is our main code that we're going to turn into a compiled piece of firmware to put on our chip. This is going to include files from the SDK. So in this example on the right, I'm looking to include the ch554.h file and the debug.h file. And what I'm doing is, by calling these files, I'm loading all of the definitions that are in those files that are specific to my chipset. So an example of that would be this P3 dir PU. This is a specific definition that's in the ch554.h file that is calling out pin 3 and a specific section of pin 3, because on these chips pin 3 has multiple sub pins, if you will. So it's calling out pin 3, the dir PU variant of that, for me to use that to tell it that it's going to be a GPIO pin. So there's different definitions in each of these files, and you can actually look at that header file to see all of those different definitions and what they are, and there's some comments in there that give you a clue as to what's what. But this is just showing you how I wouldn't know what to call it or how to address it without using the header file. That's why the SDK files are important, so that you have the header files that explain what references you're supposed to use in your code to point to different things. And then you're going to compile the code once you've finished writing it. So I have an example here on the screen where I go into one of my pieces of code and I execute the makefile, and you can see it goes through and makes all the different components of that, and then when it's done it says okay, it's done. If there were errors, it would tell me what the errors are. So where I started with a makefile and a main.c file, I have all my debug files, and I have several different compiled versions of my code, a bin, a hex, an IHX, and based on the operating system that you're on and which tool chain you're using to push the firmware to the chip, you may need different ones of these. So for example, using the WCHISP tool on Windows, I'm going to use the .hex file. But if I was using one of the Linux tool chains, I'm probably going to have to use the .bin or the .ihx, depending upon which tool. So depending upon your tool chain, that'll determine which one you use, but these are all just compilations of the same exact main C, just compiled in different ways. And so to upload the firmware, we're going to open up the WCHISP tool or whatever other tool that you're using. You're going to make sure that it recognizes your device, and then you're going to load whatever file it is that you want to put on there, and you're going to click, in this case they call it download. I call it upload because I'm taking it from my machine and uploading it to the chip, but that's a relative term, so some people call it downloading it to the chip. However you reference it, you're going to click the download button and it's going to push it to the chip, and then it'll let you know if there's any kind of errors. So with that, let's take a look at some code that I have here. So I have the code for my 84 badge. That's this particular badge, and it's using a CH552G chipset here. And so I'm going to take that code and I'm going to upload it to my badge. So we have a main.c and a makefile, and let's take a look at that code real quick before we upload it. So we'll go into here. Let's see, the makefile is just like our other example. I'm calling the target 84 badge. I'm calling the main.c file. I'm also including the debug.c file and my makefile.include. And then in the main.c, I'm calling my HH554H file. This is the SDK header file. I'm calling the debug header file. And then I start defining LED pins. Now I'm using SBit to set certain pin values. These are kind of like sub-pin values. And then here you'll see, similar to the example I had on the screen earlier, calling out different references from the Makefile. Let's take a look at that header file. So this is the header file for the CH554. And you can see all the different definitions and what they are as I go through here. And I was looking for that P3 one. It's probably buried in here. But anyway, there's comments for every one of these that tell you what they do, exactly what is what, and if you wanted to call a specific pin or a specific function on the chip, how would you do that? What would you call it? And that's where the H file is good for that. So back to our code. After I define all the pins, I go through a while loop, and based on the LED mode, this is a variable that's set by the button, I'm going to light the LEDs up in different ways. And then I also look for a button push for the button that I defined. And all of these definitions, like the button and the LEDs, I'm defining them using values that are set up in that header file. All right, so now let us go ahead and make this. And it compiled very quickly, as you see, because it's a small piece of code, and it compiled okay. And so now what we're going to do is we're going to come over here to our tool, and we will load our code from the directory. Actually, this is not the right one. From the BSides example directory. That way we're using the code that we just compiled, and here's 84badge.hex. But if you'll see, the device list doesn't show my board yet because it's not plugged in. So what I'm going to do is take my handy USB tester device, and I'm going to plug this into this chip. Now this particular chipset requires that I hold down a button while I plug it in to put it into programming mode. So I'm going to do that. And that didn't work. It just lit it up. There we go. And so you can hear when it enters programming mode, it will make a sound on a Windows system. And you'll notice on the board, if it has LEDs, the LEDs are only going to be lit like partially while it's in programming mode. But now one thing to notice is in my device list, it shows my chip. This is the chip I just plugged in on this badge, and it's a CH552G chip, but it just sees it as the 552 series. It doesn't care if it's a G or a T, because that's just how many pins are on it. And so I already opened up my file, so what I'm going to do is click download. And if we go back through these logs, we can see what it did. So the first thing it did was it loaded my file into memory, and then it connected to the device, the chip, and it erased the code that was on the device. It started programming the chip and verified it, and the whole procedure took 1.1 seconds. And it succeeded, and yeah, that's all there is to it. Now if I unplug this from programming mode, and I just use the batteries to turn it on, we will see that it is running the program that I told it to. And with this program, if I press a button, it'll change LED modes. And that one lights them all. And so that's all there is to programming in a chip's firmware via SDCC. It's just like other C compilers, it just has a lot of the hooks that you need to work with these microcontrollers. So with that, we are at the end of our presentation. I hope you enjoyed it. I hope you learned something from it. If you want to access the slide deck, it is available at altbeer.us/SDCC. And the code for what we were working on today is on the GitHub for the BSides Hardware Hacking Village. Thank you so much, and we'll see you in the next conference.